Hello, everybody, and a warm welcome to the first session this year of our Modulus Talks. I am Sophie, your host for today's webinar. For those new to our sessions, we bring together design industry experts to share knowledge and ideas, both in person at our showrooms across Europe and online. Today, we're diving into some key principles of architectural acoustics, the first talk in our three-part webinar series. Our guest is Maarten Hornix. Maarten is a professor building acoustics at Eindhoven University of Technology in the Netherlands, and he will guide us through some key topics such as sound reflection, absorption, diffusion, and acoustic materials. So let's dive in and hear from Maarten.
Thank you very much for your warm introduction, and I'm very happy and honored to deliver to you this presentation, this webinar. My name is Maarten Hornix, and I'm working with sound for more than 20 years already. So I'm working at Eindhoven University of Technology. I'm not talking much about myself and our group today, of course, but if you want to know more, you can follow these QR codes and read about my research line in the upper QR code, and also about all the research we do in our building acoustics group here at Eindhoven University of Technology. Well, architectural acoustics. If I would ask a layperson on the street or in the shopping mall, many people would come up concert halls for performance of music. And I grabbed like a random sample of concert halls. And of course, these concert halls are designed for music performance, but they are all different. How they look like, how the materials is used in these spaces. But as a matter of fact, sound is relevant for all spaces we work and live in. It is very important to know that. So it would look to an office setting where workers have work that they individually do, or they take up phone calls. Then sound is important because you don't want to be distracted. Maybe have a private call. Maybe you need to focus on your work. So disturbing sound is not very good, and also you don't want people to hear you. Another setting could be a meeting room, and especially if the meeting room is a bit bigger, you want it's very important that all people understand each all well. The acoustics of the space, so the interaction of sound with all elements in the room, plays a very important part there. So we need also to design such space as well. For focused work, reading, studying, then it's important not to be distracted. So for those kind of functions, we need to very well think about how we plan that in a space. And here you see an example of that. But yeah, not only in work environments and for music, sound in space is important, but also in the home environment. If you imagine being here and relaxing, then it's very important that, you don't want to hear too many aircrafts flying over. You don't want to hear the drilling noise of your neighbor. So the sound in your living room is very important, and may distract you, may annoy you. And eventually sound has an impact on our health, because too much sound and noise will raise our stress levels, and that reduces our quality of life. The bottom line of all those pictures is that if we work with sound, if we work with architectural acoustics, we always have to think about the function of the space. So if you would ask me what is the optimal acoustics of the room, then I immediately would ask you, where is the room tailored for? What is it designed for? Is it music? Is it speech? Is it a sports hall? And then we start thinking as acousticians what the acoustics should be. Well, if we talk about acoustics, then there's a very important concept to know. But before I go that, there's an intermezzo. I know that you have various backgrounds, so I cannot recommend a book reading for you. In case you are really interested in architectural acoustics and think after these lectures and the other 2 lectures, I want to read more, then there is very relevant books that might be of interest for you, where you find much more about what I'm talking today. The important concept that I wanted to introduce you to, it's the concept we use to quantify the acoustic quality of the room. So if we talk about architectural acoustics and indoor spaces, then the measurement of an impulse response in the room, so it's the response of the room to an impulse sound. So that could be a gunshot. Typically that's not used. Well, in the old days it was used by acousticians, as a matter of fact, to measure the quality of rooms, but it can be a hand clap, a popping balloon, and we have also very advanced measurement techniques to do that. What we measure then is how a room responds to this impulse. And at the microphone, there is a lot of sound arriving. At first, there is the direct sound, the first sound that arrives at the microphone. And after the direct sound, we have a bunch of reflections. So you see the blue line and the green line. Those arrive at the receiver after reflections with walls and with ceilings. And if you measure that, then the response of the room could look like this. So it's well, it's a complex result of all those effects. And if I would play that, let's see. So I will play an impulse response. Be aware that it may be a bit loud. And I think I have to leave the pointer now. Yeah. It sounds like this. It can sound in various ways, but in all cases, it starts very loud and then it decreases, it decays. And if you would look more in detail to such an impulse response, we would see that it has very distinct features. So at time 0, that's the time where, in this case, the gun is shot or the hand is clapped. And the first peak of the impulse response is the direct sound. Then we see distinct peaks of first reflection, but then later on it gets more messy, and then we have all interactions of the room that are causing this late part of the impulse response. These components play a role. Don't have time today to dive into that, but you can think in terms of location of a sound source. Those first reflections are very important because those determine the direct sound, and the first reflection, they determine if we as a human could localize where the sound source is in the dark, for example. We can also, apart from measuring, we can also simulate sound in a space. So here you see a computer simulation of sound propagation in a cross-section of a concert hall made by colleagues from University of Edinburgh. And you see that the sound wave, which initially was a very simple wave that spreads out spherically, it creates a very complex acoustic environment with interactions of all elements in the room. So all elements in the room, they reflect sound, they scatter sound, they diffuse sound. And today I will explain more about the interactions and how that happens on a small scale of one material. Are important because with computer simulations we can predict the acoustics of new rooms. So if we design a building, then computer simulations allow us to understand well, the acoustics of the space, and we can also listen to the space before it's actually built. We can optimize it and we can understand the behavior of sound in spaces. Now, what we can do with this impulse response. So you might think that's nice in impulse response. I understand you acousticians like that, but why is that important? Well, one important thing is that with the impulse response, we can listen virtually to any sound in that space. So how we do that is we record a sound anechoically. So an anechoic recording is a recording that we do in a room with no reflections. So you see this lady singing in a room, and this room is tailored not to be reflective. So the sound picked up by the microphone is only the direct component from her mouth to the microphone. If we have that, and we have the impulse response, we have the two components that allow us to listen to this sound in any room. So I have 4 examples for you, and this is not a voice that you will hear, but you will hear a trumpet. So a trumpet sound has been recorded in an anechoic room, and then with the measured impulse responses, we are able to listen to that sound in the rooms. It helps us to understand how the rooms will acoustically respond differently to such a musical instrument. I will play the sounds, and again, be aware this may be a bit loud, so if it's loud, please reduce the volume of your loudspeaker or your headphones. It's a trumpet in a sports hall. This is a trumpet in a concert hall. This is a trumpet in a big lecture room. And in a small lecture room. I think you have been able to hear the differences. So these kind of analysis not only give us a lot of information, looking at impulse responses as acousticians, but it also helps to transfer, to make audible, to oralize acoustics in any space that everyone would be able to grasp. Okay, but of course there's much more we can do with impulse responses. But before that, I will something about how we design a space. So I already said we need to look at a function of the space. Then after we know its function, we can, with information about the impulse response, we can say something about its quality. But if we are going to design a space, we first need to start with some principles. Before we dive into all the acoustic parameters and details of materials, there is layout issues. So if I would start designing a room, the first thing is that depending on the function of the room size, the shape, the layout, and with the layout, I mean the functioning. So if you have like a large office space, it's important to look at the functions in the office. So if there's people that collaborate, I would not put them in the same corner as the people that have to be very do focused individual work. So having a smart layout already helps to match the acoustics to the need of the room. The lines of sight, for example, in a concert hall is important, and screening and shielding of sound. If you want people that have speech privacy, it's important that they are shielded from other people. So that is, for example, a screen in between offices. So the design criteria are very important to start from. I will not talk much about them. I will talk about the use of materials today, because the use of materials is the second thing you do, and it's of immense importance. If we rate the quality of a room, we can do that in many ways. The acoustic quality of the room you can express by these attributes. You can say that the room is very spacious, or the room sounds very loud. You could say something about the speech intelligibility of the room. Well, that's nice, but how do you quantify that then? Now, with this impulse response, we are able to quantify these attributes, and there's even more, in terms of measurable values. And you see here a big table of all types of quantities, room acoustic parameters that we can measure, and we can give rooms qualities for their function. I will not go through them, all of them today, but you have an idea that there's a lot we can look at and analyze as regards room acoustics. But what I will do is I will explain you the most important parameter in room acoustic. And the most important one is the reverberation time. So the reverberation time describes the decay of sound after the impulse is ignited, so after the hand clap or the popping balloon, with 60 decibels. So in impulse response, what I've shown you before, if we take the logarithm of that, I will not exhaust you with technical details, but if we take the logarithm of that, we look to the 60 decibel decay of sound and the time it takes for the 60 decibel decay. That's the reverberation time. And of course, I'm sure that all of you recognize that if you clap your hands in the church, it takes a long time for sound to decay. That's a long reverberation time. Whereas if you stand in in a smaller room, like a living room, well, if you do that same thing, the sound will decay much faster. And this reverberation time is a very important parameter, because if it's too long, for example, and we are in the meeting room together, we cannot understand each other, or we have to talk slowly on purpose. But if it's too long for sports hall, it's the same thing. So the reverberation time is a very important parameter to work with. Some examples. So for concert halls, there is targets for reverberation times. So every function, living room, office room, restaurant, there's target values for reverberation time where acousticians can work with. So here you see Concertgebouw Amsterdam, and the concert hall in Amsterdam has around 2 seconds reverberation time for different frequencies of sound. In Eindhoven, we have a hall, also around 2 seconds, and also the very famous Symphony Hall in Boston, which is almost 140 years old, also has a reverberation time of 2 seconds. And acousticians have worked with those reverberation times to reach values that are supporting the function. And of course, for these type of halls, there's a range of variables to look at. But reverberation time is an important one. Actually, it's the most important acoustic parameter. Here you see in the ceiling, you see ways to damp sound. So there's panels that damp sound. And reverberation time is important, and it's inversely proportional to the total sound absorption in the room. So I say that again, the reverberation time, so the time it takes sound to decay, is inversely proportional to the total sound absorption in the room. So the more absorption we have, and absorption, I will explain how we can reach that in my next slides. But if we have panels, if we have material on the wall or on the ground that absorb sound, the more absorption we have, the lower the reverberation time. The harder the materials are, the lower the absorption and the larger the reverberation time. So here you see a clear link to materials. So if we have a too long reverberation time, we have to add more sound absorption, and the other way around. So sound absorption. A sound wave, and if you remember that nice animation I've shown you before, a sound wave hits a lot of walls during propagation in the room, and that incoming sound is reflected. It's reflected back in the room. But here it comes where sound absorption occurs. It's not reflected completely. Only partly part of the sound is reflected. Part is also transmitted. That's what your neighbors hear when you're shouting in your living room. But also there's a part that is absorbed in the material. And the physical mechanism here is that sound is transferred into heat. So acoustic energy, sound waves, are converted into heat. It's not very important any further because it's not creating a lot of heat. We cannot use that any further. There's very little heat, but it's absorbed. And there's various materials that can help us doing this job. And a very classical one is porous materials. So any material that has open pores does absorb sound. Sound can enter in these pores, and in the pores, this conversion from acoustic energy to heat is occurring. So that could be wood wool, foam glass, mineral wool, polystyrene, glass wool, and any type of material with that has some porosity absorbs sound. How does that work? Well, here you see some more technical scheme. On the left, this is the shaded area is representing a heart wall. In front of the heart wall, we have a porous layer. That could be one of those, any type of porous material. And now is an important thing. So what you see here is a loudspeaker. So imagine sound is produced, and a sound wave is hitting the boundary and reflected. The sum of that incident sound and the reflected sound is this pattern of this blue pattern. So it's an interference pattern between the two sound waves. So more in detail, this represents the vibrating air when sound is propagating through air. Now, if air vibrates and sound is propagating, then if we damp those vibrations, we damp sound. Well, we can damp the vibrations the best when they have its highest values. This pattern is not a pattern, an example. This is actually what is happening in reality. So what is happening in reality, if sound hits a hard boundary, then on the boundary, the vibrations are low, and a bit off the boundary, we have high vibrations. The position where we have these high vibrations depends on the frequency. Now, this example is 1000 hertz. I will play you how 1000 hertz sound tone sounds like. That's 1000 hertz. A 1000 hertz sound wave has a wavelength of 34 centimeters, and this point where it vibrates most is at 85 millimeters, 8.5 centimeters. So for an efficient damping of sound, we need to damp it at least until this spot. So that means that we need a porous material with this size. If we go to a lower frequency, 500 hertz, that frequency has a different wavelength. So it has a longer wavelength. So the lower the frequency, the longer the wavelength. For this wavelength with 85 millimeters, we have not reached this maximum vibration point in air. This is 500 hertz. So we need to have more material. And more material can be either like this, so we can have a thicker package of porous material, but you can already see 17 centimeters, that's quite much of porous material. What we also can do, and that's a very smart thing, is to have a layer of porous material at the point where we have high vibrations. Curtains are a very good example of that. So if you place curtains in front of a wall, you are able to damp sound at lower frequencies. So showing this in a different way, I show now the absorption, sound absorption. So here on the vertical, this is a graph. On the vertical axis, you see the amount of sound absorption. This is the sound absorption curve, a schematic way for a porous material. The porous material has a higher sound absorption for higher frequencies. This axis shows the frequency. It has a lower absorption for low frequencies. But if the thickness, this D, if it increases, then this curve shifts to the left. So with a porous material, we can damp sound absorption at high frequencies very well, but if we want to damp low frequencies, we would need a thick package of material. Well, what helps us is that we have other ways to damp sound, and that is a panel absorption. So here you see a scheme with a hard wall, a porous material, and then a panel in front of that. The mechanism here is that the panel is vibrating. It's vibrating on the air layer behind it. And when this system is at resonance, then at that frequency we have highest absorption. So this is an example. There's many examples you could find of a panel absorber. So this product has a rigid, like a panel here and an air layer behind, and it has this resonant mechanism. Another absorption mechanism you find, and I'm sure you also recognize that, is panels with slits or holes in it. And behind that, you will also find an air cavity and a porous layer. And also this together will absorb quite much sound, and it has a benefit of absorbing at lower frequencies than with the porous material only. So if I would summarize that, I again have a curve where I can show you the sound absorption of various materials. The yellow curve is the porous material. So that's a porous material attached to a hard layer, mostly damping sound at high frequencies. The panel construction, the resonant panel, can be tailored for low frequency sound, but not for high frequency sound. And the perforated panels do very well in the mid frequency. So this is a toolbox that an acoustician has to influence the sound absorption in a room, and with that, the reverberation time. Now, until now, I only showed you the effect of a plane surface. So if you look to this left figure, you see that an incident sound is reflected, and it's reflected in a mirrored way. So the angle of reflection is the same as the angle of incidence. Well, that's nice, you would say, but why are you showing that? Well, there is surfaces that the surface shape determines how sound is reflected. So if you have this convex surface, then sound is spread in multiple directions. A concave surface, on the other hand, focuses sound. In a whispering gallery, or if you have ever be below a dome surface, sometimes you recognize that it sounds very loud, and that's because of focusing effects of sound. But what I wanted to show mostly is this example. So this surface is very, at first sight, random. It has like random surface shape, and this causes sound to be scattered in multiple directions. So sound scattering means that sound that hits a surface or object is not reflected in this way, in a mirrored way, but it's reflected in a more diffuse way. Now, why is that relevant? Well, at first, maybe this concept is still a bit hard, but look at this example. I took just an example I could find for light. It's an analogy. So you recognize that if you paint a wall, you can choose the paintings, if it's very glossy, or if it's very even in reflection. Well, for light, this is also an image source reflection almost. If you have a light below this paper, you would see where the light is, and here you don't see that. But for light with very high wavelengths, the roughness of this material is very low. For a sound, we need more roughness, so you get surfaces like this. But why is that relevant, you would say? Well, if we have a room like this, the sports hall that I already showed you before, we could have a flutter echo. I will play this sound. This is an impulse response, and what you hear is that the sound is decaying, but it's also going back and forth, back and forth, back and forth, back and forth. And that's because sound is reflected back and forth between two parallel walls. This can be very annoying in a sports hall if you're playing ball games and you continuously hear the ball hitting the ground being reflected back and forth, or if you want to your teammates or your trainer be heard, then flutter echoes are not good. If you apply scattering material to the walls, then you avoid flutters, because then sound is not reflected back in the same direction and so on and so forth, but it's reflected everywhere. There's other examples where this could be of relevance. If you have a living room which is very minimalistic, then you can have parallel walls, and well, they cause flutter echoes, but if the rooms are smaller, they also amplify the sound quite loudly. Especially in small meeting rooms, this can be very annoying, that sound can be quite loud. Scattering of sound is then important to make the sound field more pleasant. And well, this is an example of how sound can be reflected in a diffuse way. And there's a lot of products like this, but sound diffusion does happen with objects that are relatively small. So if you see this, the living room, then if you would add other like furniture, like bookshelves, if you add something on the walls, then all those materials will add more diffusion to the sound field. So if there is a scenario where the sound field needs some scattering, where you need to diffuse the sound field more, then you may think about very dedicated surface like that. But it also helps to think about like everyday furniture or plants scatter sound a bit. So there's more material that can scatter sound in a satisfactory way. Another example of sound scattering, I need to see if I can go back to this slide, is in a concert hall. So I think I have the example here. The Eindhoven Hall has also some scattering elements. So you see here, it's not very visible, but here on the edges here, there's scattering elements, because otherwise people in the audience, they hear very clearly a reflection of one of the musical instruments coming from the left or the right. And then the balance of the orchestra is not good. So sound scattering elements, you also see them here, they are also used in concert halls quite much. Well, the final thing I want to take you to today is an demonstration by the effect of materials in a room. So what I will play you is a screen cast of a virtual reality demo, an acoustic virtual reality demo. So you will hear music played and also hand clapping played in a small venue for music. And while you hear this, the user of this virtual reality application can change the material in the room. The material that is changed are the walls. So I will move a bit here. No, it's not showing. Yeah, are the walls of the room. So they can be changed. And when they are changed the first time, I will pause it and I will say something more. So please relax and listen to this example. So you heard two musical instruments, and what the user has changed is you saw that these panels. So there's two type of panels. This is a wooden panel. The other panel is very absorptive. And maybe you noticed that for the piano in the beginning, the difference was not as audible as what you hear now. Less important. The reason why it's more important for this this piece of music and this musical instrument is that here the sound is more it's not continuous. So if the sound stops, then the decay of sound in the room, the reverberation plays a bigger role. But if the sound is continuous, the room does not have the time to decay every time, so you don't hear the decay of sound as good. I will continue playing, and you will also hear a hand clap, and also the user will move to different places in the room. So you will also experience how this effect of materials will change for different locations. Well, I hope that you all have experienced that the materials can have a huge influence by just this example on how you perceive sound in spaces. And we are coming to the end of this webinar presentation. I have some lines to wrap up. So the acoustic quality of a room should follow its function, whether it's the type of function that users, that's the people are using it for. It's important to use design principles for the space, for that function, so that you have an acoustic design. Then we have acoustic parameters that we can use as the reverberation time to fine tune and improve the space. And finally, material properties are key, especially absorption and the scattering of material properties. They are very important to improve the parameters and thereby the space, the acoustics of the space. Thank you very much.